Hello friends, this video on coordination compound part 28 is brought to you by examfear.com. No more fear from exam. Discuss the nature of bonding in the following coordination compound on the basis of valence bond theory. Please note we have to use valence bond theory, not the crystal field theory. Okay. So first is FeCN6, 4 minus. In this case, the charge on iron is +2. Because each of the copper Cn has -1 charge, -1 into 6 is -6, so it has +2 charge. So we talk about the Fe2 plus is 3d6. Electronic configuration of Fe2 plus is 3d6. See, this kind of theory we can actually know the answer by crystal field theory. It is easier to understand. Crystal field theory, you know that Cn minus is a very strong ligand, so it will do the pairing. Okay, but we don't know that, because the question is we have to do on the basis of valence bond theory only. Okay, in valence bond theory we don't have the types of ligands, strong or weak ligands. We have 3d6. 1, 2, 3, 4, 5, 6. Okay, 3d, 4s. Now we know that this FeCN6 4 minus is dimagnetic. This is something we know using experiment. That means this electron has to rearrange. So with that, the new configuration will be 3d, 4s, 4. Now it has to bond 6 bonds. So it will form bond 1, 2, 3, 4, 5, 6. That means it will use D2sp3 hybridization. So all this will form D2sp3 hybridization. So D2sp3 hybridization is what? Octahedral. So you can say it's an octahedral structure based on valence bond theory. Same thing if you want to write on the based on crystal field theory, is pretty easy. So it's a 6, it's octahedral for sure. So you can create 6 like this. Cn is a very strong ligand, it will force pairing. There are 6 electrons. 1, 2, 3, 4, 5, 6, because Cn is a strong ligand force pairing. So we have 2 here, right, remaining, right? 2 vacant d orbital, so it will form D2sp3 bond. Right? D2 2 vacant d orbital is free, so D2 is there, and the next is sp3 orbital. The remaining orbitals will be used, so D2sp3 orbital will be D2sp3 hybridization will exist here. It will be octahedral. So using both the theory, you can actually predict the shape. The next is F6 3 minus. Here the oxidation number of iron is Fe3 plus. We can find that. So Fe3 plus is what? 3d5. Okay, and we know this is paramagnetic. So because we have to use valence bond theory, we have to know what is the compound is paramagnetic or dimagnetic. It's 3d. So it is 5, right? 1, 2, 3, 4, 5. Then you have S, then you have P, again you have D. So this is 4S, 4P. Okay, so now we have to see, this is paramagnetic, this is known that is paramagnetic. Paramagnetic, so no pairing, because it has to have unpaired electrons, and thus the 6 electrons that has to come. We'll use 1, 2, 3, 4, 5, 6. In fact, 6 into 12 electrons, because each of this fluorine will donate 2 electrons. So 12 electrons will come in this 6 orbitals. So it will be sp3d2 hybridization, and that is nothing but octahedral. So it is octahedral in shape based on valence bond theory. Using crystal field theory also pretty easy. 6 is octahedral. We know this is the kind of structure. This is T2G and this is EG. This is something we know. Fluorine is a weak ligand, it won't force pairing, it will be in this form. There is no vacant d orbital for 3d. Then the next orbital that will be used is 4s, 4p and d orbitals for bond formation. So it will form sp3d2 hybridization, that is octahedral. Okay. The next is COC2O4 3 minus. Here if you see 3 into 2 didentate ligands, coordination number 6, octahedral. If you want, you can confirm on this. Here the cobalt will have oxidation state of +3. Plus +3 minus 6 is -3. So cobalt plus 3 is 3d6. Cobalt is 3d7 4s2. This is 3d6 4s0. If you want, you can write that. 3d6. 3d 4s 4p. Okay. 6 1 2 3 4 5 6. Okay. Now it is known that this is again paramagnetic. So if we do a pairing, what will happen is the paramagnetism will be lost. This is something we know experimentally, it is paramagnetic. So we want to the pairing, correct? So we want to the pairing, so it will need 6 orbitals to form 6 bonds. Coordination number 6, 1, 2, 3, 4, 5, 6. So it will form sp3 d2 hybridization, and that is nothing but octahedral. Using valence bond theory to explain that. Okay, using crystal field theory also you can explain. You can just say that this is a weak ligand, it won't do pairing, so it will use this octahedral. You can write something like this, and this is a 6 electrons, 1, 2, 3, it won't do pairing, 4, 5. Here there is no choice, it has to do pairing 6. You see there are 4 electrons here, the d orbital is filled, so it will use the next sp and d orbital, that is sp3 d2 hybridization, it will be octahedral. Okay. Next, take COF6. Here oxidation state of cobalt is again plus 3. So cobalt plus 3 we know is 3d6. Again similar to that, similar to the last example. Okay, this is 3d, 4s, 4p, 6, 1, 2, 3, 4, 5, 6. And if you see that experimentally it is seen that this is also paramagnetic, so it won't do pairing, so it will use the next 1, 2, 3, 4, 5, 6 coordination number, right? So it will use sp3 d2 hybridization for bonding bond, and it will be octahedral. Okay. The next question is, what is spectrochemical series? Difference between the weak field ligand and strong field ligand. Please know, weak field ligand and strong field ligands. Spectrochemical series is nothing but arrangement of the common ligands, common, not all, in the increasing order of their crystal field splitting energy values. And that is determined experimentally. Please note, this value is determined experimentally. So in this case, if you see, carbonyl has the maximum value for the crystal field splitting energy. Iodine minus has the minimum value. So this is, let's suppose, I minus, and this is CO minus. And this I am talking about the octahedral complex. For the octahedral complex, if my carbonyl is the ligand, it will have maximum splitting. This energy is more. Here, this energy will be less. Okay, so based on the experimental value of crystal field splitting energy, this series has been determined. It is useful to calculate or extrapolate the structure of various coordination complexes. Okay. What is crystal field splitting energy? How does the magnitude of delta naught decide the actual configuration of d orbital in a coordination entity? See, crystal field splitting energy is nothing but the energy between these two d orbitals, right? So typically we have degenerate d orbitals. All the orbitals in the d, all the 5 d orbitals, all these 5 d orbitals are in the same energy level in absence of any ligands or electric field, right? So when in the presence of ligands or electric field, these orbitals break into various parts depending on if it is octahedral or tetrahedral. This is the example I am taking for octahedral. Okay, so this degenerate orbital, this degenerate d orbital actually splits into 2 parts. So if you see here, it was degenerate, it splits into 2 parts, right? So this is 2 and this is 3. Okay, but octahedral in this case, this is T2G and this is EG. This is dxy, yz, xz, and this is x square minus y square and z square. So this split into 2 levels in the presence of ligand. This splitting of the degenerate orbitals in the presence of ligand is called crystal field splitting. Okay, So energy between these two levels is called crystal field splitting energy. This delta naught is called crystal field splitting energy. And after this split, fulfilling of electron take place, or filling of electron takes place. See, first 3 electrons will come here. Okay. Now the question was, how does the magnitude of delta naught decides the actual configuration? O is octahedral, so they are also talking about the octahedral scenario here. First 3 electrons will come here. Okay. Okay. So let's see how this delta naught or the crystal field splitting energy makes a difference. Example in this case, anyway, in both scenarios, let me draw the box here. Each box have one orbital. In this case, the energy difference is less. First 3 electrons will anyway, in both scenarios, will come here. Now the 4th electron is a tie. It may come here or it may pair. Now in this case, the energy difference is not that much, so the 4th electron will come here. But in this case, the energy difference is more, so the electron will pair. And that is the difference. Right? So this actually, the difference in energy decides the actual configuration of d orbital. Right? So after the 3rd electrons are filled in this T2G, these are T2G. The 4th electron may either go to EG or may pair in T2G. This will depend on delta. So if the delta naught is higher than P, pairing energy, here delta naught is higher than P, here delta naught is less than P, less than the pairing energy, then pairing will not happen. So delta naught is higher than P, the pairing will happen. Okay, and this will actually decide the configuration of the orbit. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.